Welcome back to the series on linear algebra. One of the challenging things about this subject is that there's so much necessary background information before you can have one of those big picture moments where everything comes full circle and you really understand what the subject is about and why it's so important. Because of that, a lot of people will go through a linear algebra course, no pun intended, but linearly, and by the time they have all of the requisite knowledge, they're so far removed from the subjects where it would be illuminating, or the topics where it would be illuminating, that it never just clicks, the puzzle pieces don't fall into place, and linear algebra has a tendency to be pretty unmemorable for a lot of undergraduate students, despite the fact that this is probably the most important field of mathematics, at least right now. So to mitigate this, I want to try to create one of those moments early on in the course. So my promise to you is by maybe the end of this video, but definitely by the next video, I'm going to try to give you that big picture moment where everything comes together. But in order to do that, this video is going to seem a little bit jarring. So in the last video, we talked about statements. I'm going to put that perspective on the back burner for now. And in this video, I'm going to talk a lot about functions. And also in this video, I'm going to have to introduce a lot of new things. So it's going to feel like I'm jumping around. It's going to feel sporadic. It might even seem a little bit random, but I'm telling you this now, a little disclaimer that all of this is deliberate, and I'm setting everything up so that I can give you one of those moments early on, and hopefully that really intrigues you about linear algebra and makes you want to learn more. So let's get started. Maybe you might be wondering why it's called linear algebra in the first place. What's distinct about this course, this subject, that makes it different from, 8th grade algebra or whenever you took it? Linear algebra is the focus of linear functions, and we need to start talking about what this word linear means, because you're probably thinking y equals mx plus b, the equation of a line, but in linear algebra and in general higher level mathematics, linear has a special meaning. So we say a function, f, is linear if and only if for any inputs x and y and numbers alpha and beta, we have that f of alpha x equals alpha f of x, and f of x plus y is equal to f of x plus f of y. Or, and this is the same thing, f of alpha x plus beta y is alpha f of x plus beta f of y. Now, these are the same thing because if this were true, if both of these things were true, then I could write this as f of alpha x plus f of beta y, just using this fact right here. You take any two inputs, then you can add the together like that. And so you could just treat these as two inputs, and you can separate them according to that fact. And then you can just apply this fact onto each of these. And this translates to alpha f of x plus beta f of y. And so sometimes it might be easier to show these facts separately, and sometimes it might be easier to show them at the same time, but these two things are equivalent. Now, you might be wondering why these linear functions are special and why we have a whole field of mathematics that studies these. It's because you could take a, somewhat complicated expression like this, or there could be many more of these terms. It doesn't have to be two. There could be, 3, 4, 100, or infinitely many. And then you can break them up into smaller, more manageable pieces like these. And sometimes these smaller pieces are much easier to compute. And so linear functions are very nice because of that. And let's actually look at an example so that I can show you how this makes things easier. So I want you to pause the video and try to do this on your own. We're given that definite integration is linear, and the integral from negative infinity to 0 of e to the negative t squared dt is square root pi over 2. And we're asked to solve this integral right here using those facts. So I want you to try to solve this on your own. Give it a shot. If you're not able to solve it, no worries, because I'm going to do it in a second. All right, so hopefully you tried to do that, and hopefully you either were successful or you got some progress done. So the first thing to do is that we're going to take this integral and we're going to break it up. And I'm going to break this up into the integral from negative infinity to 0 of 3 e to the negative t squared dt. And then I'm going to say plus the integral from negative infinity to 0 of negative 4 e to the t dt. And now I'm going to simplify this further by pulling these constants out of the integral. So I'm going to do 3 times the integral from infinity to 0, e to the negative t squared dt, minus 4, I'm just going to pull that negative 4 out, the integral from negative infinity to 0 of e to the t dt. And now this integral right here is given to us. It's the same as this one right here. So now we could just plug that in and we're done there. And let's just deal with this integral right here. The antiderivative of e to the t is e to the t. And so this is just e to the t evaluated at negative infinity and 0. And so if you evaluate this at 0, you get 1. If you evaluate it at negative infinity, you get 0. So this is just 1. And so we get 3 times the value of this integral, which is given to us, square root pi over 2. And then this one is just 1, so this is minus 4. And we're done. Oh, missed that a little bit, but now I want you to pay attention to what we did. The first thing that we did is we took this integral and we broke it up into these two pieces. And we can do that because definite integration is linear. That is exactly this property right here. That's what we did. We took the operation evaluated at 2 inputs added together, and we broke it up into the operation evaluated those inputs added together. And then what did we do next? Well, we had these two pieces here, or I'm sorry, these two pieces here, and we pulled out that scalar quantity, and that's just this fact right here. That's this one. And so we use those facts about integration, the fact that it is a linear operation, in order to break this complicated puzzle into much smaller, much more manageable pieces, and that let us solve the integral in like 2 lines, given this background information. So this is why linearity is so useful. We never had to take the antiderivative of this function. And indeed, that would actually be impossible because this integral is impossible. This is impossible to anti-differentiate. It's undefined. And so we took a problem that would otherwise be impossible, and we used this information in order to solve it because linearity makes things easier. All right, so I'm going to do one more example here. When you heard linear before a linear algebra course, you probably think of a equation of a line. This f of x is equal to mx plus b. So let's check if that's a linear function. And so in order to check that, we have to show that the function satisfies that f of alpha x for any alpha and any x is equal to alpha f of x. And we have to show that f of x plus y for any valid inputs x and y is equal to f of x plus f of y. So let's just try to show this one first. And so what's f of alpha x here? Well, that's just going to be m times alpha x plus b, which is equal to alpha mx plus b. And what's alpha f of x? Alpha f of x here is equal to alpha times mx plus b, which is equal to alpha mx plus alpha b. And so these two things are not equal. And so this property does not hold, and f of x is equal to mx plus b is not linear. Now, you might think that maybe it's the intercept term that's throwing things off, because that's what's not equal. These two things are equal, but this is not equal. And so let's check if f of x is equal to mx is linear. And in order to check that this is linear, I'm just going to try to do both of these at the same time. I think if you're trying to show that something is not linear, it's usually easier just to show them separately. But if you're trying to show that something is linear, it's easier to show them together. I guess I knew that this wasn't going to be linear, but either way, they're equivalent. So let's take f of x is equal to mx, and let's evaluate f of alpha x plus beta y. Okay, so for mx, this is equal to m times alpha x plus beta y. And this is equal to, we just distribute m alpha x plus m beta y. And that's equal to alpha mx plus beta my. And this is equal to alpha f of x plus beta f of y. So f of x is equal to mx is linear. So hopefully that clears things up. It's important to understand when we're talking about linear functions, we're not talking about equations of a line, we're talking about something more specific. And if you don't have an intercept term, then the function is linear, as we just showed. But if you have that intercept term, it's not linear. Okay, hopefully all of that made sense. Now I want to introduce something called linear combinations, which is very highly connected to linear functions. We say that y, and I want you to consider y as a possible input to a function, is a linear combination of some set of other possible inputs to that function, x1, x2, all the way up to xn. If there exist numbers, alpha 1, alpha 2, all the way up to alpha n, such that y is equal to alpha 1 times x1 plus alpha 2 times x2 plus alpha n xn. So basically y is just some combination, some weighted combination of x1 all the way up to xn, then it's a linear combination. And why is this special? It's because if we have a linear function, if f is linear, then what's f of y? Well, f of y then is just f of alpha 1 x1 plus all the way up to alpha n xn. And then just by linearity, this is alpha 1 f of x1 plus all the way up to alpha n f of xn. And so the reason that this is special is because if we know the value of some linear function evaluated at each of these things that makes up y, you could call this the basis for y, for example. If we know the function a linear function evaluated at each of these, then we immediately know that function evaluated at any linear combination of these just by the definition of linearity. Because if we know what these alphas are, then we can find the value of the output of any linear combination. And so I know that sounds really abstract, but let's look at an example to see if we can make sense of this, or see if we can make this easier to understand. Trying to get this in the right spot. So we're asked to find the area under an arbitrary degree 2 polynomial from 0 to 1. And so this is not an easy problem, but I want to show how this connects to this idea of linear combinations and linear functions. So we know that definite integration is a linear function. It's a linear function that takes another function as input and outputs a number. So I want you to consider that. Definite integration is a function. It takes another function as an input and outputs a number. So I want you to consider the inputs to definite integration as the following. I'll say that x3 is equal to 1. Actually, I want to be clear. x3 is a function. So I'm going to write x3 of t is equal to 1. x2 of t is equal to t. And x3 of t is equal to t squared. Okay, I know this might seem confusing, but I'm just writing these things. I meant to put x1 right here as well. I know this might seem confusing, but these are the possible inputs to integration. Okay, so now I want to consider if f, let's let f of x be the integral from 0 to 1 of x of t dt. Okay, so f is a function. It's going to integrate another function, x, from 0 to 1. So it's a function that's going to map one of these other functions to a number. Okay, so what's f of x3? Well, f of x3 is the integral from 0 to 1 of x3 of t dt, and this is equal to the integral from 0 to 1 of 1 dt, which is just equal to t evaluated 1, which is 1. Okay, what's f of x2? Well, this is equal to the integral from 0 to 1, x2 of t dt, just by definition. And this is equal to the integral from 0 to 1. What's x2 of t? Well, that's right here. It's just t dt. So this is t squared over 2, valued at 0, 1, which is 1/2. Okay. Now I want to evaluate the function at this other possible input, f of x1. Okay, so just again, here I'm going to skip a step here. I don't think this is necessary. This is going to be integral from 0 to 1 of t squared dt, which is t cubed over 3, evaluated 0 and 1, so this is 1/3. Okay, so at this point, what we have is we have these possible inputs to the function being integration from 0 to 1, and we evaluated that function at each of those. Now we know that integration is a linear function. So now what I want to do is I want to show, or I want to solve what is f of ax squared, or no, I'm messing this up. At squared plus bt plus c. That would be an arbitrary degree 2 polynomial, and this is the same as f of ax1 plus bx2 plus cx3. And just by linearity, this is a f of x1 plus b f of x2 plus c f of x3. F of x3. And because we already know these values, then we can use this fact of linearity just to immediately solve this. This is just a over 3, because that's a times f of x1, which is 1/3, we just computed it, plus b over 2, which is just b times f of x2, which we already computed, plus c times f of x3, which is just 1, so that's just c. And we're done. So what did we do here? Well, we had 3 inputs, 1, t, and t squared, and from those you could take a linear combination. This right here is a linear combination of these 3 because a, b, and c are just numbers, and so this is just some weighted combination of these 3 things. And so that's a linear combination. This is a linear combination of those, but this represents every possible degree 2 polynomial. And so the point here is that we can find the area under any degree 2 polynomial, an arbitrary one. Just by finding the area under these 3, we can find the area under all of them. All of them. And it's this. All right, so I hope you enjoyed that example, and I hope that shows how linearity is super useful. We can evaluate a function at some small set of inputs, and then from just that, just evaluating those, in this case 3 things, we get infinitely more information by considering a linear combination, which actually looks like something useful here. And so the kind of the goal of linear algebra is to break up problems into ways in which we can use linearity to make them easier, and then get a bunch more information out of just a few things. So it's really useful. But in order to do more with linear algebra, we need to introduce some more stuff. So we need to talk about matrices and vectors. And after we introduce these things, I know it's going to feel like I'm jumping around, but it's going to make more sense. All these ideas I just talked about are going to make even more sense. So let's jump into it. All right, so we'll start with matrices. Matrices are just a mathematical object that's a way of organizing numbers. And so they're represented as these grids with square brackets around them. It might be a little confusing as to why this is useful until we start to see how we use them. So for now, they're just grids of numbers. These are some special shapes of matrices that you are going to want to be able to recognize. They're all extremely intuitive. So you have a square matrix where the number of rows is the same as the number of columns. You have a rectangular matrix where the number of rows is different from the number of columns, which can happen either way. And this is an upper triangular matrix, this one right here. And upper triangular means that the entries below the main diagonal here are all zeros. So we see that here. Then we have the lower triangular. That means that the entries above the main diagonal are all zero. And again, pretty intuitively, a diagonal matrix has entries that are non-zero only on the main diagonal. Everything else is a zero. Dimension is an attribute of these matrices that tells you the size, and it's represented as the number of rows by the number of columns. And so this is a 3 by 3 matrix, this is 3 by 2, this is 2 by 3, and then all of these other ones are 3 by 3 matrices. So number of rows by number of columns. All right, so that's what matrices look like. And now to actually use them, we need to talk about some operations that we can do with matrices. And the first and simplest is matrix indexing. And that's when we want to get a particular number out of this matrix. And so a matrix is a grid. And in order to define a specific entry in the matrix, you need to specify the row and the column. And the way we do that is we define the row first and then the column. And so when I write this, that tells me to go to the matrix A, the first row, and the second column. So I go to the matrix A right here, go to the first row and the second column, and the value, the entry that corresponds to that is going to be 8. And similarly, if I want to get the value stored in the second row and the third column of the matrix, I just go to the second row and the third column, and that's going to be this value here, the value 0. And so hopefully that makes sense. We can just do the rest of these pretty quickly. And so if I want to get the value in the third row in the second column, that's going to be 9. And the fourth row in the first column, you can look at this matrix, there's no fourth row. And so this actually does not exist. Does not exist. And then the last one here, we go to the first row in the fourth column, and we get the value 3. So hopefully that's pretty simple. The next thing that we need are addition and subtraction, or really just addition for matrices, and scalar multiplication. The reason we need these two things is because we want to be able to use this idea of linear combinations with respect to these matrices. That's going to be much more natural, arguably, than some of these ideas I've expressed before of like polynomials, like representing an arbitrary degree 2 polynomial as a linear combination of the different terms, the powers. That's a little bit, usually that's more complex than understanding these linear combinations of matrices and vectors. So we'll look at that in a moment. But for matrix addition and subtraction, you add together each of the elements entry-wise. So you compare each element. For instance, in this matrix and this one, we want to subtract these. And so we do 1 minus 1, and we're going to get a new matrix. It's going to be 0. 3 minus 0 is 3. 4 minus 0 is 4. 0 minus 0 is 0. 2 minus 2 is 0. 6 minus 0 is 6. 0 minus 0, 0 minus 0, 8 minus 3 is 5. And similarly, if we want to multiply a matrix by a number, this is the number 8, then you just multiply each entry. So this is 8, 16, negative 16, and 32. Again, we want to be able to define these things because we want to use linear function. We want to be able to say these functions act linearly on vectors, and in order to do that, we need to show those facts from before, that f of alpha x plus beta y equals alpha f of x plus beta f of y. And in order to show things like this, we have to be able to talk about addition of vectors and scalar multiplication of vectors. Here, x and y would be the vectors in matrices. Now, of course, because this is how we chose to define vector and matrix addition, I guess I haven't told you what a vector is, but a vector is really just a special case of a matrix. I'm going to tell you right here, actually. But because this is how we've defined matrix addition and scalar multiplication, adding, subtracting matrices requires them to have the same dimension. If we're going to add and subtract every single entry, then they have to be the same shape. For instance, I can't do 1, 2, or plus, like, I don't know, a 1 by 1 matrix, which just has a single number in it. I can't add these together because I would have to be able to add each entry, and this only has an entry in the 1, 1 spot. Okay, so now I can tell you what a vector is. These are just matrices. A column vector is a matrix with one column, and a row vector is a matrix with one row. And so these matrices here are column vectors because they have, this one has 3 rows, but it only has one column, 2 rows, only one column. And then these two are row vectors because they only have one row. So it's 1 row and 3 columns, 1 row, 2 columns. And we don't need 2 indices. We don't need 2 indices for a vector because we only need to specify, for a column vector, we only need to specify the row. And for a row vector, we only need to specify the column. So if you have a vector, like for instance, this u is a vector, then in order to index into it, we only need one number. So when I write u3, that's going to tell me the entry in the 3rd row, which is a 7. We also have this operation that is specifically for vectors called dot product. The dot product of 2 vectors is computed as the sum of their element-wise product, which we can write in this way right here. Hopefully you've seen summation notation before, but what this means is I'm summing this quantity, but I'm going from I is equal to 1 to n. And so I'll show you what that looks like with an example. But this essentially is u1 v1 plus u2 v2 plus u3 vt all the way up to un vn. I guess I should write that if in the case that you haven't seen summation notation before, u2 v2 plus u n vn. This is just a much more compact way to write that same idea. The dot product has a few geometric interpretations that make it more intuitive why this has a special name. But it's going to come up even in this video in just a moment when we talk about matrix multiplication. And so I just think we should do an example because that makes it easier to understand. If this is my vector x1 and this is a vector x2, we want to find x1 dotted with x2. And so we take the element-wise product. So I look at the first entries and I multiply them. We have 1 times 8 plus the second entries 2 and 10. So I do 2 times 10 plus the third entry is multiplied 3 and negative 3. And so I get 3 times negative 3. And so this is 8 plus 20 minus 9, which is 19. Is that right? Yeah, I think that's right. And so this is the dot product here. One geometric interpretation, for instance, if I have the vector, let's say u is equal to the vector 1, 2, and I want to plot this, that would be 1 to the right and 2 up. This is one way that we could plot vectors. They look like this. You draw them with little arrows. And so this vector goes 1 unit to the right and 2 units up. And if I did the dot product of u with itself, then this would be 1 times 1 plus 2 times 2, which would give me 5. But more importantly, that's the length of this side of the vector here, the horizontal component squared, plus this side, the length of the vertical component squared, because this is 2 and this is 1. And so what this is telling us, if you remember from Pythagorean theorem, the whole c squared is equal to a squared plus b squared. And here this would be a, this would be b, and this would be c. C here is the length of the vector, and so this is going to give us the value of c squared, the dot product of the vector with itself. And so the square root of u dotted with itself gives you the length of the vector. And similarly, if you take the dot product of 2 different vectors, there's a way to show that it's related to the angle between the 2 vectors. So this is an important thing, but we'll talk more about that later. For now, we're just going to need this definition so that we can use it when we talk about matrix multiplication, which we're going to do shortly. All right, so we define matrices and vectors, and you're probably wondering why we're talking about this in the first place. So I want to go back to our system from the last video, this x plus y equals 5 and negative 5x plus 7y equals 18. And in the last video, we saw that these equations are statements, and we can modify this system of statements using only specific operations that preserve the truth value of these statements in order to produce an equivalent system of statements that told us something more useful. It told us the identity of these unknown variables. But in this video, what I want us to recognize is that we can completely characterize a system of statements or system of equations with three distinct parts. The first are the coefficients. And the next part are the unknowns. This is your x and your y in this case. And the third part is, I'm going to call it the right-hand side. So this is our 5 and 18. And if you know all three of these pieces, then you've completely characterized some system. And what I want to do is I want to write these three pieces for a system using matrices and vectors. And so I'm going to define a matrix A that's going to contain our coefficients. So in this case, that'd be 1, 1, negative 5, and 7. I'm going to define a vector, and if you want to be explicit that you're talking about a vector, you can put an arrow above it. And this is going to be the vector of unknowns. So this is x and y. And then I'm going to also use a vector to write the right-hand side. I'm going to call it B. This is just standard convention, but that's going to contain our right-hand side. Now, you'll note that in the last slide, I didn't write anything about matrix multiplication. I talked about scalar multiplication of matrices. If I want to take, this matrix A and multiply it by a number, we know that we can just multiply every entry by that number, and that gives us the result. But what I want to do is I want to define matrix multiplication, but I want to define it in a special way. And the way that I want to define it is I want A times x in this case. I want this to equal a vector, and I want it to be x plus y, and I want it to be negative 5x plus 7y. So this is a column vector. It's 2 by 1, and the entry in the first row of this column vector, I want it to be the first left-hand side, and the entry in the second row, I want it to be the second left-hand side. And if I'm able to define matrix multiplication like this, then what that means is I can take this system of equations, this system of statements, and I can write it instead as one big statement. I can write it as A times x equals B. And that's what I want to do, because this lets me very succinctly write out this system of equations. And you could think, okay, for a 2 by 2 system, this isn't so bad, for a 2 by 2 system, it's not so bad to write out all of these equations. But as this gets bigger and bigger and bigger, we want to be able to use a computer or something to solve these problems, and it's much more simple to store something like this in a computer. And also, it's just easier to write. And we could talk about things in this way, and then we don't actually need to write anything out. We could just define these variables like I did right here. And so hopefully you could see this. If I say A times x is equal to this right here, and I set this equal to the vector B, which is this one right here. To say the two vectors are equal is to say that each of their entries is equal. So this is the same as saying x plus y equals 5, which is this statement right here, and negative 5x plus 7y equals 18, which is this statement right here. So that's why those are the same. Hopefully that makes sense. And so what I need is I need to define matrix multiplication in a way such that if I take this matrix, negative 5 and 7, and I multiply it by this 2 by 1 matrix, but this vector, it is just a matrix, then I want to get x plus y in the first entry, and I want to get negative 5x plus 7y the second entry. Now, if you just kind of consider where we started with this system of equations here, oops, not sure how that happened, but if we just consider where we started with this system of equations right here, you recognize that if you look at this coefficient matrix, we want this column to be scaled by x, and we want this column to be scaled by y for obvious reasons. And so the natural way to define this matrix multiplication is to say that we want this result right here to be a linear combination of the columns of this matrix. And so in other words, what we want is we want this to equal the entry in the first row, which would be x of this vector, and we want to multiply that by this column of this matrix. So I'm going to do x times 1, negative 5, and then I want to take the entry in the second row and I want to multiply it by the second column. 1 and 7. And this obviously follows very naturally from this. Here you have x multiplying the left and then y right there. And so this is a natural way to define it, and this would indeed give you the vector that you want. This is completely correct. 5x plus 7y. Now, another thing to notice is that there's another way to look at this. So if I kind of get rid of these, the way that we were looking at it is that these are the coefficients that go on x, and these are the coefficients that go on y, and we just want to add them together. That's that sort of column idea. But the other way to look at it is to say that if I look at the first row of this matrix, this tells you the coefficient on x and y in the first equation, and this tells you the coefficient on x and y in the second equation. So the second way that I could define this, if I just sort of copy this down here, the second way that I could define this is I could say, okay, we're going to look at the first row. I'm going to multiply the first number times x and the second number times y. And I'm going to add the result together. And if you remember, that's just, I'll be explicit here. This is 1 times x plus 1 times y. And if you remember, this is just the dot product of two vectors. And if I look at this, if I want the second entry here, then I'll look at the second row, and I'll say, oh, this is the coefficient on x, this is negative 5 here, and this is the coefficient on y. And so I'll just multiply the first number times the first entry, and the second number times the second entry, and I'll add the result together. And so this is the dot product of the second row with this column vector here. And this does indeed give us the result that we want, x plus y and negative 5x plus 7y. So both of these ways to look at it are equally valid. In one way, we look at the columns of the matrix and we scale them by the variable that we're looking at. So we look at each column and we see that as the coefficients on each of these unknown variables. The second way is to look at each row of the coefficient matrix as the coefficients of each of these values, and then to take the dot product to add them together and get the equivalent left-hand side. But both of these are equally valid ways to look at matrix multiplication. All right, hopefully that's making sense, but if not, just bear with me. I'm going to talk about the formal definition, and then I'm going to give some examples, and hopefully that will make everything more clear. So formally, when we talk about matrix multiplication, if we have two matrices A and B, then the ijth entry of the matrix product, which we write as AB, for example, just like with normal numbers, it's going to be given by the dot product of the ith row and the jth of the ith row of A and the jth column of B. And so just like in this example here, when we wanted the ijth entry of this matrix product, AB, let's say we wanted the first and second entry, so this would be the first row, or sorry, I meant the second first entry, so this would be the second row in the first column, which would be this entry right here. Then this is going to equal the dot product of the second row of A with the first column of B. So if I look at the second row of A and the first column of B, and I take the dot product, then I do negative 5 times x plus 7 times y, which is this right here, and I get this entry. And if I write that, So one thing to note is that in order for this dot product to be defined, the length of the rows of A must equal the length of the columns of B. If they're not the same, then we can't take the dot product. For instance, if this was like a 3 by 1 vector, we had a z here, and I wanted to take the dot product, I would do negative 5 times x and 7 times y, and I'd have nothing to multiply by z by. So those dimensions need to match. And so formally, what we and I guess I should note the length of the rows of this matrix here is just the number of columns, right? That's how long the rows are. And the length of the columns of this matrix is just the number of rows. And so another way to say that is that the number of columns of A must equal the number of rows of B. So hopefully that makes sense. That's what I'm saying right here. For the dot product to be defined, the columns of A, the number of columns must equal the number of rows of B, for the reasons I just stated. So formally, if A is an m by n matrix, meaning the number of columns is n, and the length of the rows is the number of columns, it's all n, and B is an n by p matrix, meaning the number of rows is n, and analogously, the length of the columns of B is n. Then that means the length of the rows of A matches the length of the columns of B, and so we can do matrix multiplication. And it's formally going to be defined in this way, which is going to make more sense with a picture. So I'm going to draw 2 pictures here, or I guess I'll draw 1 picture, but one is going to be the matrix A. I'll give myself lots of room in the matrix B. And I'm going to move this up a little bit so I can use column. And so in this matrix A, we're going to have m rows. So I'm going to go 1, and then we'll go down, and there'll be some row I here, and we'll go all the way down. And the last one will be m. And then for B, we're going to start at column 1, and then there will be some point here where we'll reach column J, and we'll go all the way down to column P will be the last one. And in this row, we'll have A, I1, A, I2, and we'll go all the way down to A, I, N. And then in this column of B, the jth column, we'll have B1J, B2J. We'll go all the way down to B in J. Okay, so with this picture in mind, I'm going to say that the ijth entry of AB, the ijth entry of AB, is going to be given by taking the product of the entries in this row with the entries in this column, and then summing up the results of all of those. And so what is that going to look like? Well, first we'll take these two, AI1 and B1J. And so this is going to be AI1, B1J, and I'm multiplying those two things together. And then I'm going to add to that the product of these two entries, B2J and AI2. So AI2, B2J. And so I'm going down across this row of A and down this column of B, and I'm taking these entries and I'm multiplying them together. And so the next one would be AI3, B3J. And we'll just keep going in this fashion until we reach the last entry here in this row and the last entry in this column, which will be the same number of entries because we've defined the length of these rows to equal the length of these columns, and then we'll add that product there, AIN, B, N, J. And so this is going to tell us the ijth entry in this row. If we wanted the 1-1 entry, then we'd go across the first row of A and the first column of B, for instance, and we do the same thing. But this is a very awkward way to write this, and the much more succinct way to write this is with summation notation. So we can sum from k equals 1 to n of aik bkj. So we start at k equals 1, we'd have ai1 b1j, and then we add ai2 b2j, and you can see that that's the same thing that we have right here. Another way to write this is with the dot product, and so this is the same thing as the ith row of A multiplied by the jth column of B. It's the same thing. And I don't think I've discussed this yet, but I can talk about this right now. This T symbol right here is the transpose. And so the transpose of a matrix, the transpose is just the same matrix, but you swap the rows and the columns. So I'll give you an example of that right now. If I have this matrix 1, 2, 3, 4, 5, 6, and I want to take its transpose denoted by that capital T in the top right corner, then I just take the rows of the matrix and I make them the columns. And so I would write a new matrix 1, 2, 3, 4, 5, 6. Here, the first row becomes the first column, the second row becomes the second column. That's pretty simple, but the transpose actually comes up a lot, and we'll see many examples of why that is the case. But if I take the ith row of A and I transpose it, so I'm taking the ith row of A, this one right here, I'm going to transpose it to make it a column vector, AI1, AI2, I'll go down to AIN, and I take the dot product with the jth column of B, B1J, B2J, down to B in J, and I'm taking the dot product, and so that just means to multiply these entries and add them all together, which is what we saw before, and you can see that this is the same thing as this. And so all of these are equivalent ways to express the formal definition of matrix multiplication. They'll give you the ijth entry of the matrix product. Hope that makes sense. And if this is still a little bit unclear, that's completely normal. And we're going to look at some examples, and I think that will solidify everything. We see it actually worked out for some different problems. All right, so I want to multiply two matrices, A and B here. And the first way that I want to do it is I want to compute it in the classical sense. And so for the first entry in this matrix, I'm going to go to the first row of this matrix, and the first column, I'm going to take the dot product. So I'll do 1 times 2 plus 1 times 3. And so that's going to be the first entry, or the entry in the first row in the first column. I forgot what this was. It gives a 2. And then if I want the entry in the second row in the first column, that entry that will go right here, then I have to take the second row of this matrix and the dot product with the first column. And so it's going to be negative 5 times 2 plus 7 times 3. Okay. And then if I want the entry in the first row and the second column, I need to take the first row of this matrix and take the dot product with the second column. That'd be 1 times 1 plus 1 times 1. And then for this last entry here, this entry in the second row and second column, and you take the second row of A and the second column of B and take the dot product. And so that's going to give me negative 5 times 1 plus 7 times 1. And if I add all these together, I get 2 plus 3, which is 5. I get 1 plus 1, which is 2. And here I get negative 10 plus 21, which is 11. And then I get negative 5 plus 7, which is 2. And so that's the way that you would multiply this together in these two matrices in using the formal definition, for example. But now I want to look at this matrix multiplication in some different ways. So the first thing I want to do is I want to consider the first column of B only. And we could multiply this out in the way that we just did, and we could get a result. But there's another thing to recognize, which is that this looks just like our system, except instead of x and y here, I have 2 and 3. In the last example, it was x and y. And we saw that a more natural way to define this that doesn't invoke any summation notation or anything like that is just to consider this as a linear combination of the columns of this matrix. And so we can write this as 2 times the first column, 1 and negative 5, plus 3 times the second column, 1 and 7. And if you're not convinced that these are the same thing, then just look, when I do the formal matrix multiplication, I'll take this row dot product with this column, and then in the second one, I'll do this one times this column, this row times this column. And every single time, I'm taking the entry on the left side here, and I'm multiplying it by 2. And every single time, I'm taking the entry on the right side here, and I'm multiplying it by 3. And so if I do that just more explicitly, I take 2 times the left entries and 3 times the right entries. I add them together. I should get the same thing. And what happens here? Well, this would be 2 and negative 10. And then here we get 3 and 21. And this gives us 5 and 11. If you notice, this is the first entry, or the first column of the result. This is the first column of that result there. And so what this is telling us is that the columns of the matrix product, the columns of the matrix product are going to be given as linear combinations of the columns of the matrix A, and the coefficients of that linear combination are given by the columns of the matrix B. So another way to say this is that the first column of AB will be 2 times the first column of A plus 3 times the first column of B. And we can check this if we want to look at the second column of AB, then I'm going to take, these will be the coefficients, and so it'll be 1 times the first column of A, 1 and -5, plus 1 times the second column of A, which is 1 times 7, and I get 2 and 2, which is exactly the second column here. And so this is another way to look at matrix multiplication. We can say, okay, the columns of the matrix product are going to be a linear combination of the columns of the matrix on the left here, the matrix A, with coefficients given by the columns of the matrix, the second matrix. And now let's look at the second row of A only. The second row of the matrix A only. And so I'm taking, remember, this is the matrix A, the one on the left, and so I'm only looking at this row. If I do this matrix multiplication, then what's going to happen? Well, I'm do it just the way that we always do it. Then if I look right here, -5 is going to multiply the top number. And if I look at the second entry, -5 is going to multiply the top number. 7 is always going to multiply the bottom number. And so, I can rewrite this as -5 times the first row, 2, 1, plus 7 times the second row. And what is this going to give me? This will give me -10 and -5, plus, and then what am I going to get here? 21, 21, and 7. And so I get 11 and 2. And what do you know? This is the second row of the matrix product. And so when we look at this, we could look also as the matrix A is going to tell us combinations of the rows of B that will give us the rows of the matrix product. And so if I want to look at the first one, then I can look at the first row of this matrix A, and this tells us to take 1 copy of the first row of the second matrix and add 1 copy of the second row of the second matrix, and that will give us the first row of the matrix product. So if I take this row and I add it to this one, I should get the first row of the matrix product, and I do. 2 plus 3 is 5, 1 plus 1 is 2. And again, just to reinforce this, if you look at the second row of the matrix A, it's going to tell you the coefficients for a linear combination of the rows of matrix B. So this tells us to take -5, multiply it by the first row of A, and 7, multiply it by the second row of B, add those together, and I will, just like I showed, get 11 and 2. I'll get the second row of AB. All right, so hopefully that made sense, and that gives you 3 different ways to look at matrix multiplication. Sometimes the row method is easier, sometimes the column method is easier, and sometimes, very rarely, the formal definition is the easiest. But they're all useful, so it's important to understand all of them, and the only way to really understand is to practice. But let's look at some properties of matrix multiplication. Again, we have some notation I need to introduce. So when you write this as a mathematician, it tells you alpha is in the real numbers. So all this is telling you is that alpha is a real number. It's a number. And when I look here, I'm writing A is in the real numbers with dimension m by n. And all of this is telling you is that A is an m by n matrix. And this is telling you that B is a n by p matrix. It's just a much quicker way to write it, so I'm going to start introducing that now. And we want to show that if I take the matrix A and I multiply it by a scaled copy of the matrix B, that's going to be that same scalar factor multiplied by the matrix product AB. You can see this is like the first component of showing that this is linear. And so in order to show this, we'll just consider the easiest way to do a lot of these matrix proofs is to show, if you could show that the ijth entry, if you could show what the ijth entry of a matrix is, just for an arbitrary I and j, then you completely know everything about that matrix. And so I'll show you what that looks like. So I want to show that the ijth entry of the matrix formed by A times alpha B, want to show that the ijth entry of this, well, let's just consider what this is. This is the ith row of A dot product with the jth column of alpha times B. And so if I write that explicitly, this is going to be the sum from k is equal to 1 to n of A I k times the matrix A B k j. And what's the kjth entry of this matrix? Well, that's just alpha times, when we do this scalar multiplication, we take alpha and we multiply every entry. So this is just alpha times the b kjth entry, the kjth entry of B. And so I can rewrite that as alpha times b kj. I'll just get rid of the parentheses. Alpha times b kj. And then now these are all just numbers. This is the entry in the matrix, this is the entry in the matrix, and this is a number. And so now we can just flip these around however we want. And so I'm just going to pull the alpha outside of the summation since it's multiplying every single number. And this is going to give us this result right here. But this right here, this is just the ijth entry of the matrix product AB. And so this is equal to alpha times AB ij. And we're done. We just showed that for an arbitrary ijth entry of this matrix, which is this side right here, it's equal to an arbitrary ijth entry of this matrix, which is this one right here. So that's true for every index of the matrix. So these two matrices are equal. And A times alpha B is equal to alpha times AB. I hope that made sense. Let's look at the next property that we want to show. This would be like the second component of linearity, like that f of x plus y is equal to f of x plus f of y. And here the function here would be multiplying by the matrix A. I want to show that A times two matrices is equal to f of B plus f of C, where f is multiplying the object by the matrix A. And so we want to show the second component of linearity here. And so how are we going to do this? Well, we just need to show that the ijth entry of this matrix is equal to the ijth entry of this matrix for all I and j, just like we did in the last example. So we'll start by considering the ijth entry of this matrix. So A times B plus C ij. What is this going to be? Well, we're just going to take the dot product, and so we're going to sum from k is equal to 1 to n, and we want to go over the rows of A. So I want the row index to stay the same, but I want the column index to change as we index to the right over the row. And so it's going to be aik times, and then I want the matrix B, the matrix B plus C. I want the kjth entry of that matrix because I want to go over the columns. And so I want the row index to increase as I go down the matrix, but I want the column to stay the same. Hopefully you can picture that. So this is going to be the matrix B plus C, kj, the kjth entry of that matrix. Now, we've already defined adding two matrices. We know that when we add two matrices together, that we're just adding the entries in the same spots. And so we would add the entries in the first row and the first column together. We'd add the entries in the second row and the second column together, second row's first column, etc. For all of the entries, we add them entry-wise. And so the kjth entry of the matrix B plus C is just going to be the kjth entry of B plus the kjth entry of C. That's what that is. That is what that is. And we're multiplying by aik, summing from k is equal to 1 to n. And now, these are all just numbers. These are entries of the matrices, so these are numbers, and so ordinary rules apply. And so we can use the distributive properties to say that this is equal to k is equal to 1 to n of aik bkj plus aik ckj. And then I can sum up numbers however I want. I could sum all of them together inside of, I could sum each of these individually together, or I could break this up into two sums, because at the end I'm just going to get one number and it's going to be the sum of all of these terms. So I could break this up however I want, and I'm going to break it up like this. I'm going to take this as two sums. I'm going to sum aik bkj, and then I'm going to sum the rest of the terms, all these AC terms. So this is going to go from k equals 1 to n of aik ckj. And when I break it up like this, it becomes obvious, because this is just the ijth entry of AB, and this is the ijth entry of AC. And so with that in mind, we can rewrite this. That just comes from the definition of matrix multiplication, but that tells us that this is equal to AB ij plus AC ij, and this is just the ijth entry of AB plus AC, of the matrix AB plus AC. And so I showed that for an arbitrary ij, the ijth entry of this matrix, A times B plus C, is equal to the ijth entry of A times B plus A times C. And so this property does hold. If I have a matrix A times matrix B plus C, then that's equal to the matrix A times the matrix B plus the matrix A times the matrix C. All right, we have one property left to show, and this one is a little bit harder, but I think we got it. And so once again, so here we have three matrices. A is n by n, B is n by p, and C is p by q. And so we can do A times B times C. And I want to show that A times B times C is the same as A times B times C. And so once again, we're going to start by just showing the ijth entry of this matrix is equal to the ijth entry of this matrix for all I and j. And so we'll start by considering the ijth entry of the matrix A times B times C. And so what is this going to be? Once again, we're taking the sum from k is equal to 1 to n, because we're summing over the rows of A and the columns of B. And we're going to sum over the rows of the ith row of A times the jth column of B times C. And so the jth column of B times C. This is kj. And what is BCKJ? Well, this is just the sum from, I need to use a different index here, L equals 1. We're going over we're doing the kth row of B dotted with the jth column of C. And so we want to sum over the kth row of B. And so we want BKL. We want to stay on the kth row, and we want to sum to the right. And we're going to sum over the columns. We're summing over the row of B, so we're taking each column of B. We need to go over the full length of B. And so we're going to sum from L equals 1 to P. Hopefully that makes sense. So we're going over the kth row and the jth column of C. So C, L, J. We want to hold the column of C constant. And so that's what that sum is. You have to be careful with the indices here. And so this is going to equal the sum from k is equal to 1 to n a I k times the sum from L is equal to 1 to P of B K L C L J. And now note that this value here does not depend on the index L. And so we can just multiply it. When you multiply the whole sum by a value, it's the same as multiplying each individual term by that value. That's just the distributive property. And so this is the sum from k is equal to 1 to n. The sum of L is equal to 1 to p. And this is a I k times b k l c l j. And now these are just numbers. And so the order in which we multiply numbers does not matter. Each of these is just an entry in a matrix. And now I want you to recognize that we're summing over a bunch of numbers. Each of this is just three numbers multiplied together. It's just going to give you a number. And so we're summing some combination of all three of these numbers, but in the end, we're just going to get one big number that's the result of the sum of all of these terms. And so the point that I'm trying to make is the order in which we sum these things up does not matter. It doesn't matter if I sum from L equals 1 to P first or from K is equal to 1 to N first. We're going to sum over all the terms regardless. And so I can swap these two no problem because addition is commutative. And so when I swap those summations, I go from L equals 1 to P. This is completely valid. And I go from K equals 1 to N of A I K B K L C L J. And now note that this C term does not depend on K. And so I can pull that out of the summation, kind of working in the opposite direction as I did when I started. I'm going from L equals 1 to P of C L J multiplied by the sum from K equals 1 to N of A I K B K L. Now note that this summation here, just by the definition of matrix multiplication, this is the I-elfth entry of the matrix AB. And so I'm going to rewrite this as the sum from L is equal to 1 to P of CLJ times AB IL. And this is the same as the sum from L equals 1 to P of the I-elfth entry of B, because this is just a number times CLJ. And this right here, this is the ijth entry, of AB times C, because we're summing over the ith row of AB and the jth column of C. And that's exactly what we wanted to show. We showed that the ijth entry of A times BC is equal to the ijth entry of A times B times C. And so this property of associativity holds for matrix multiplication as well. Okay, so hopefully you followed the logic of these three properties that we showed that they hold. This is typically the hardest part for a lot of people in linear algebra, so I'm trying to introduce it early so we can start to get used to these ideas. The big idea is that if you're trying to show that two matrices are equal, it's very often easier to just show that for an arbitrary ijth entry, their entries are equal. Because if you show that for every entry, then the matrices must be the same. But again, we'll get better with practice. And so now I want to talk about some special matrices. And in all of these cases, I don't want to use the formal definition of matrix multiplication in order to see what these are. So the formal definition was very useful for these proofs. It helped us to show that two matrices were equal because we could show the ijth entry, and the way that we expressed the ijth entry of these matrices was using that formal definition, summing over the ith row of A and the jth column of the matrix B times C, for example. But in general, if we're just doing a matrix multiplication, it's very often going to be easier to use that column idea or that row idea. And so just as an example here, I want to talk about the identity matrix. This is a diagonal matrix where only ones are on the diagonal. So there's going to be zeros above the diagonal, zeros below the diagonal, and the only entries we're allowed to have on the diagonal are ones. And the way that I want to do this matrix multiplication here is I want to use the row column, the row picture. And so if I look at the result of this, I know that the first row of the resultant matrix is going to be given as a linear combination of the rows of this matrix with coefficients given by the first row of our matrix on the left. And so this is just telling us to take one copy of the first row of this matrix, and that's going to be the first row of the result. And so that's just 1, 2, 3, and 4. And this tells us that the second row of the result is going to be one copy of the second row of the second matrix. And so this is just one copy of the second row. And so we get 8, 6, 10, and 1. And you could probably see the pattern here. This matrix multiplication is not changing the matrix because we're just taking, for the first row, we get one copy of the first row of this matrix. The second row, we get one copy of the second row of this matrix. The third row, the result is one copy of the third row of that matrix. And so we're just copying the rows. This isn't going to change anything. And this is much easier, in my opinion, to see and understand than it is to actually do the matrix multiplication. And similarly, if I multiply with the identity matrix on the right side, then now we're looking at the column picture. The first column of the result is going to be one copy of the first column of the left-hand side. And the second column of the result is one copy of the second column, that side. So we're just copying the columns over. And so that's why we call this the identity matrix, is because it's not changing the matrix when we multiply by it. It copies it over. It leaves everything the same. 3, 10, 3, 9, and 4, 1, 2, 7. Keeps it the same. So that's the identity matrix. Now I'm going to talk about the zero matrix. This is the matrix of all zeros, and sometimes they denote that with a bold 0. But I'm probably not going to do that because it's hard for me to write bold on here. And so what's going to be the first row of the result? Well, it's just going to be 0 copies of the first row of this matrix plus 0 copies times the second row of that matrix. And I mean, surprise, surprise, this is just going to be all zeros because it doesn't matter if we multiply on the right or the left by this matrix, because when we multiply on the left side, we're taking 0 copies of the first row, and on the 0 copies of the second row, and we're doing that for all the entries. We're taking 0 copies of everything. But if I multiply on the right side, then I'm taking 0 copies of this column plus 0 copies of this column. And so I'm doing that for everything. It's always going to be all zeros. That's the zero matrix. And now I actually want to use our brains a little bit. And so I want to show you how quickly we can compute these matrix multiplications. Obviously, these are like special matrices where it just by design is supposed to be easy. But if I want the first row of the result here, then I know it's going to be 0 copies of the first row of the second matrix plus 0 copies of the second row plus 0 copies of the third row. So it's going to be 0, 0, 0. And the second row is going to be the same, 0, 0, 0. But the third row is going to be 0 copies of the first row of this matrix plus -2 copies of the second row plus 0 copies of the third row. And so rather than actually doing the matrix multiplication and trying to see what this matrix is, I could just say that, oh, I know the third row of the result is going to be -2 times the second row of this matrix, which is going to be -6, -8, and -16, and I'm done. Similarly, if I would do this matrix multiplication here, I know that the first column of the result is going to be 0 copies of the first column of this matrix plus 0 copies of the second column plus 0 copies of the third. So the first column of the result, I know, is going to be all zeros. And the same is true for the third column of the result. And the second column of the result, I know, is going to be 1 copy of the second column plus 1 copy of the third column. So all I need to do to get the second column of the result is add these two columns together, and I get 53, I get 19, and I get -17. And I'm done. I don't have to do a whole matrix multiplication. So this is what I mean when I say sometimes it's easier to use the row idea, for instance, in this matrix multiplication, and sometimes it's easier to use the column picture. For example, if I wanted to use the row picture with this matrix multiplication, I would do, okay, I need I need 18 times this row, I need 20 times this row, and I need 33 times this row. And then I would do that for each of them. And that's just much more difficult than looking at the column picture, which gave us 2 0 columns, and then 1 simple addition for the second column. And obviously the same is true for this matrix. Here, the row picture is easier because you get 2 0 rows, and then we get our third row is just a scaled copy of the second row here. And so that's why I want to emphasize that we want to understand all of these ways to do matrix multiplication, because when we're actually multiplying matrices, it's easier almost always to use the row or the column picture. And when we're trying to do these proofs, we're trying to show different properties, it's easier to use the formal definition because that tells us what a arbitrary index of a matrix equals. I really hope that makes sense. Right, so one thing that you may have noticed in these examples is that for these matrices, if I took the identity and I multiplied it by a matrix on the left, for example, and on the right, then we got the same thing. And so in other words, AI, where I is the identity, is equal to IA. I is usually how you would denote this identity matrix with ones on the diagonal. And we also notice that the same is true for the 0 matrix. For instance, if I take 0 and I multiply it by a matrix on the left, the 0 matrix, I'll try to make it bold, then that's going to equal A times the 0 matrix on the right. Because both times you're just taking 0 copies of the columns or 0 copies of the rows. And so I want to ask if, in general, AB is equal to BA. Like for numbers, AB is equal to BA. Is this true for matrices? And in order to answer this question, I want to make an observation, which is that if A is a M by N matrix and B is a N by P matrix, remember these are the conditions that we need in order to define A times B, then I want to consider what are the dimensions? What are the dimensions of A times B? Meaning, how many rows and how many columns does A times B have? And I guess the easiest way to see that is what would be the last entry? What would be the last entry? The entry in like the last spot of A times B? Well, you take the last row of A and the last column of B, and you take their dot product. And so the last row of A would be M, and the last column of P, or of B would be P. Kind of gave it away there. But basically, A times B is going to be, it's going to be an M by P matrix. Because the last entry will be the mth row of A dotted with the pth column of B. And so that's the last entry. This matrix is going to have dimension M by P. And so this is a handy thing to remember. If you take an M by N matrix and you multiply it by an N by P matrix, then the result is going to have these outside dimensions. We need these inside dimensions to be equal, and the result of the matrix multiplication is going to be those outside dimensions. This is super, super handy to remember, just to be quick. And so with all that said, we can answer this question really easily, actually. So let's just, the answer to this question is no. In general, AB does not equal BA, and I'll prove it very quickly. I'll let A be a 2 by 1 matrix, and I'm going to let, I'm going to let A be a 2 by 2 matrix, and B is going to be a 2 by 1 matrix. Then AB exists, and it's going to be a 2 by 1 matrix. It's going to be a 2 by 1 matrix because I'm going to take a 2 by 2 matrix multiplied by 2 by 1. These numbers line up, and the dimension of the result is going to be 2 by 1, just like we just talked about. But BA does not. We cannot multiply B times A because this number and this number do not line up. The number of columns of B is not equal to the number of rows of A. So that dot product is undefined, and B times A does not exist. So BA cannot equal AB, obviously. And so, in general, most of the time, It's actually only under special circumstances when AB can equal BA, and the only way that that can happen is if one of these matrices is a scaled version of the identity matrix. But that's kind of beyond the scope right now. The point is that in general, AB does not equal BA. This commutativity of multiplication property does not tend to hold for matrix multiplication. All right, in the next video, I'm going to introduce an algorithm for solving systems that's going to use matrices. And that's going to be where our big full circle moment comes together, and we're going to see how this perspective of functions and linear combinations and matrices and all of these new ideas that we introduced in this video integrates together with this perspective of statements that we were talking about in the last video, and we're going to show how that makes solving systems of equations, no pun intended, but systematic and much, much simpler, very easy. And so I hope you all enjoyed, and I hope you're looking forward to the next video.